Okay, so welcome to Homework 1, Part 1, where today we're going to be proving that the torque for a Couette viscometer, we're analyzing a Couette viscometer, that the torque at the inner cylinder is equal to the torque of the outer cylinder, given some starting expressions. And let's move to the iPad so I can demonstrate that. Quick overview. Couette viscometer is essentially a device that measures the viscosity of a fluid by two concentric cylinders, where the inner cylinder is spinning around, torque applied by an electric motor, and the outer cylinder is static. Okay, now back to that thing about torque. Well, that intuitively makes sense, right? If the outer cylinder is static and there is a torque applied to the inner cylinder, it would only make sense that there needs to be a counter torque on the outer cylinder to keep things static, right? We're also given a number of expressions. First and foremost being our velocity profile. This velocity profile is different from what we've seen before. We have worked with velocity profiles in the past where we assume that the two cylinders are basically planar, which we can say that the velocity profile is linear. However, with this we would get a much more accurate picture. This is the velocity profile for two concentric cylinders. With angular velocity, omega, big R, our outer radius, and R, our radius where we're analyzing our velocity, right? And we also have K, where K is simply the ratio of inner radius to outer radius. Next, we have an expression for shear rate, and shear rate is defined as the velocity profile divided by R, taken to the derivative with respect to R, and the whole expression, multiplied by R. And finally, we have Newton's law of viscosity, which states that the shear stress is equal to the viscosity multiplied by shear rate. Okay? Well, okay. We also, we can hop right into it. We can start. Remember, we're balancing the torque, so we're saying that the torque inner somehow, some way, must equal the torque outer. And let's take a look at the most simple definition of torque, which is that it is a force multiplied by a lever arm. Force multiplied by a lever arm. In this case, lever arm is R. Some radius R. Wow, I'm really messing up the eraser. So some radius, lever arm R multiplied by the force. Okay? Remember that our goal here is to try and get this in these terms as much as possible. So that starts really with force. That's nowhere in our starting expressions. How do we relate that to viscosity? And in this case, how to relate it to shear stress? Well, you can recall that shear stress has same units as pressure, where shear stress is equal to force per area. Therefore, we can say that the force is equal to shear stress times area, right? Shear stress is, by Newton's law of viscosity, is defined as the viscosity multiplied by the shear rate, and now we have multiplied by area. At this point, I can just go ahead and say, well, don't overthink it. The area of contact for the fluid is simply the outer shell of the cylinder, so it's 2 pi RH. Gather up our variables. We have torque is equal to, and I'm going to do this in a way that's convenient for me. Okay? There we go. It's the first useful expression. Let's start analyzing the torque at the inner radius. So we first have to find shear rate at the inner radius, okay? And let's look at our expression for shear rate. So velocity profile shear rate, let's do this in purple. Shear rate over R. So let's slowly build from inside out. Our expression for shear rate. So if we divide our velocity profile by R, well, we just have omega k squared over 1 minus k squared times r squared over r squared minus 1. Okay? If you take the derivative, Still on purple. Take the derivative of that with respect to r. Well, then we have omega k squared 1 minus k squared. Remember? That's all constant. It's not r, so it doesn't get touched. Multiplied by r squared over r cubed. Well, we also have a negative 2 up front. Oh, and this 1, it's multiplied by the constants up front, and if you're differentiating, well, that just gets canceled out, right? Finally, we multiply that whole expression by r to get our shear rate. Oops. So now we can say that shear rate is equal to negative 2 omega k squared over 1 minus k times r squared over r squared over independent variable r squared. Now, let's look at this from the perspective of the inner cylinder. So we can define the independent variable r as the inner radius. So, let's say that actually, let's go off to this. See that the shear rate at inner radius is equal to 2 omega k squared over 1 minus k r squared over ri squared, right? What does it look like? It's a ratio of outer radius to inner radius. Well, we have the ratio of inner radius to outer radius, so therefore this is k reciprocal squared, inverse k squared, right? This is actually 1 over k squared. Now that cancels out, so we're left with our expression for shear rate at the inner radius is equal to negative 2 omega 1 minus k. Okay? We can now plug this into our expression for torque and say that, well, torque at the inner radius is equal to 2 pi viscosity times height. Well, negative 4. Actually, for simplicity's sake, let's keep things here and we'll simplify later. Y minus k. Oh, this should be squared. 1 minus k squared r I squared. Okay, if we're analyzing torque at inner radius, the independent variable r will become the smaller radius, the inner radius, right? Pulling out our constants, we then have negative 4 pi mu h omega ri squared all over 1 minus k squared. There is our expression for torque at the inner radius. Okay? Let's look at torque at outer radius. Before we do that, we have to look at torque at shear rate at outer radius. So let's take a look at that. Now we say that the expression for shear rate at the outer radius for independent variable r is equal to the outer radius. Well, that just goes to 1. We then have 2 excuse me, 2 omega k 1 minus k squared, right? Looks a little funny, and we can plug it into our expression for torque, and it'll still look funny, but I assure you it works out. Okay, remember this is our shear rate at outer radius. So now, let's keep this red. Now we say that our torque at the outer radius from the expression we derived earlier is equal to 2 pi mu times height negative 2 omega k squared over 1 minus k squared. And this time it's radius at the outer edge, so big R. Let's gather up our constants, see if that helps. Hint, it doesn't. So negative 4 pi mu times height is equal to, oh sorry, not equal to, times omega k squared r squared over 1 minus k squared. Oh, not quite the same, right? Not quite the same. we have to do some simplification here. What do you notice? You notice that I put this deliberately, that k squared being right next to r squared. We can expand our k expression. Recall that the k expression is equal to the ratio between the inner radius and the outer radius, and if it's squared, both is squared, multiplied by r squared. That cancels out. In reality, k squared times big R squared is equal to inner radius squared. Inner radius squared. Or I squared. Look at that. It matches up. It looked bleak at times, but it matches up. We now have our two torques at the inner and outer radius balanced. So that concludes part 1 of homework 1.